2.2 Steady State Exercise by MARC KENNEALLY. The test we are carrying out as a group is to see the effects of steady state exercise on the body and how it changes during and after steady state exercise. The activity will be carried out by 3 individuals that will each participate in a 20-minute bike ride, and the results will be recorded during the activity. Steady state exercise is when the performer is taking part in physical activity for a long period of time or working at the same intensity. The intensity of the exercise should be about 65 to 70% of your maximum heart rate. There are 3 types of hypothesis. There is a null hypothesis, two-tailed hypothesis, and a single-tailed hypothesis. A null hypothesis is a general statement that there is no relationship between 2 measured groups. A two-tailed hypothesis is a test of a statistical hypothesis where the region of rejection is on both sides of the sampling distribution. It is called a two-tailed test. For example, suppose the null hypothesis states that the mean is equal to 10. The alternative hypothesis would be that the mean is less than 10 or greater than 10. Single-tailed hypothesis is a test of the statistical hypothesis where the region of rejections is on only one side of the sampling distribution. It is called a one-tailed test. For example, suppose the null hypothesis states that the mean is less than or equal to 10. The alternative hypothesis would be that the mean is greater than 10. The hypothesis for the cardiovascular is that during steady state exercise our heart rate will plateau after an initial increase, as there is enough oxygen for our muscles to continue working at the same intensity. Therefore, the blood doesn't need to be pumped around the body as much in order to deliver the oxygen to the working muscles. Respiratory. The rate of breathing will increase at the start and plateau after about 2 minutes. Energy system. The systems used at the start would be ATP and ATP-PC energy systems. This would then switch to the aerobic energy system, which would be the predominant energy system. Before the test, the participant will warm up on a bike to get used to working the muscles they'll be using in the test. The warm-up would consist of a 2 to 3 minute gentle bike ride, and it would also raise the heart rate and breathing rate of the performer. The method for the cardiovascular. In order to measure the heart rate throughout the test, we would use equipment. In this case, we used a watch and a heart rate monitor, which we would use to tell what the performer's heart rate is during the exercise. We will measure the heart rate every 2 minutes so that we can gain data for our hypothesis. Respiratory. The breathing depth can only be measured using a gas analysis, which is a very expensive part of equipment, and therefore we aren't able to measure in depth. In order to measure the breathing rate, we will count the amount of breaths per minute. We will do this once every 2 minutes, as this can be used for data. If it fluctuates, then the performer is working too hard or not working hard enough. So if our hypothesis is correct, the breathing rate should stay constant. Energy system method. We will measure the participants' oxygen levels and lactate levels. We will do this by taking blood samples. We would measure this before the test, during the test, around 10 minutes, and straight after the test. If our hypothesis is correct, then the oxygen levels should be higher than the lactate levels. The heart rate hypothesis. I believe that the heart rate will increase at the start of exercise and then will plateau after a few minutes. Why will this happen? Initially, heart rate increases due to the proprioceptors detecting the movement, and the chemoreceptors will detect the lack of oxygen. A message would be sent by these receptors to the cardiac control center, which is located in the medulla oblongata in the brain. A message is then sent down the sympathetic nervous system to the SA node, which as a result will increase the heart rate. The heart rate will plateau after the increase due to the working muscles getting enough oxygen during steady state exercise. Therefore, the heart rate doesn't need to get more oxygen around to the muscles, and the heart rate no longer needs to increase. The reference is Prezi for this. Stroke volume. Stroke volume is the amount of blood pumped out of the left ventricle per beat. The average stroke volume is around 70 milliliters at resting, and the stroke volume of an elite athlete is 90 to 110 milliliters at resting. Initially, the stroke volume will increase. It would then plateau during a steady state exercise. This is because the heart will contract stronger and therefore pump out more blood during each contraction. Therefore, stroke volume is increased during exercise. It would then plateau as the heart will beat at the same intensity as it can get the blood around the body, meaning there is no reason for it to contract any stronger. As a result of this, the stroke volume will remain constant and will therefore plateau. Unfortunately, we won't be able to measure this, as we can't measure the amount of blood pumped out of the heart per beat. The reference for this is also Prezi. Cardiac output. The cardiac volume will increase at the start of exercise and will plateau during the steady state exercise. Cardiac output is the amount of blood pumped out of the heart in 1 minute, and therefore will increase due to a large increase in heart rate and a smaller increase in stroke volume. This means that more blood is pumped around the body in 1 minute, and so more oxygen is able to get to the working muscles. The cardiac output will then plateau due to the body working aerobically and at a steady pace, meaning it is able to get the amount of oxygen around the body which is being demanded and doesn't have to work any harder, so stays constant. We are also unable to measure this during the activity. The average cardiac output for an adult is about 5 litres per minute at resting. However, an elite athlete like Mo Farah has a cardiac output amount of around 3.63 litres per minute. The reference for this was Medicine McGill. Blood pressure. Before exercise, there will be an increase in systolic blood pressure and it will plateau during the exercise. However, the diastolic value will only change slightly. The blood pressure will increase due to the dilation of the blood vessels in active muscles, which increases the vascular area for blood flow, and the contraction and relaxation of muscles forces blood through the vessels and returns it to the heart, which increases blood pressure. Blood pressure is the pressure of circulating blood on the walls of blood vessels. Systolic blood pressure is the blood pressure when your heart beats, and diastolic pressure is when your heart rests between beats. The reference for this is Pearson Schools and FE colleges. Blood flow. Blood flow increases at the start of steady state exercise as the working muscles are demanding more oxygen. This is why the heart rate also increases, and therefore more blood will be pumped around the body in order to get the amount of oxygen needed to the working muscles. The body contracts the blood vessels going to some parts of the body, such as organs, which we don't need as much oxygen at that point in time, and redirects the blood to dilate other blood vessels going to working muscles. This is why blood flow increases. The precapillary sphincters close at non-essential organs, and blood is directed to working muscles, which increases blood flow to the essential organs. When the blood vessels contract, this is known as vasoconstriction, and when the blood vessels dilate, it's called vasodilation. The blood flow would then plateau as the working muscles would be getting the oxygen needed, and therefore the blood flow can stay constant. After the exercise, the blood flow will decrease again, as the body and muscles don't need as much oxygen, as they don't need to work at the same intensity. and therefore not as much blood is needed to be pumped around the body and through the blood vessels. The vascular shunt is when the body distributes blood around the body. This would occur during steady state exercise. The blood vessels going to organs and body parts we don't need to experience vasoconstriction, whereas the blood vessels going to the muscles we will need experience vasodilation, as more oxygen is needed in these areas and less blood is needed in the places where vasoconstriction takes place. This is explained by earlier when I talk about the precapillary sphincters. The reference for this is prezi.com. Thermoregulation. Thermoregulation is the process of maintaining the body's temperature. However, during exercise, the body produces a lot of excess body heat. The body temperature is then maintained and kept constant by removing the excess heat. The excess heat is lost through sweating and through the blood vessels expanding, which is also known as vasodilation, so that blood passes close to the surface of the skin. As the sweat evaporates, it cools down the skin. This is how the body maintains a constant body temperature. Therefore, during steady state exercise, the level of sweating increases, meaning thermoregulation is required. The reference for this is also prezi.com. Venous return. There is an increase in venous return during steady state exercise. This is because the flow of blood back to the heart is needed after it has been distributed. This is because when venous return is restricted, the left ventricle receives less oxygenated blood. Therefore, if it is increased, then more oxygen can be distributed to the left ventricle. Starling's law. Starling's law is a theory which states that stroke volume increases in response to an increase in blood volume filling the heart. This stretches the ventricular walls, causing the cardiac muscle to contract more forcefully. Stroke volume may also increase due to stronger contractions in the cardiac muscles during exercise. Therefore, the reduced heart rate of a trained athlete allows for greater filling during the longer diastole. So the stretch of the cardiac muscle is greater. This, in turn, increases the stroke volume. The reference for this is Pearson Schools and FE colleges. Energy systems. The main energy system that will be used is the aerobic energy system. This is because the body is working at steady state, meaning that it will be able to work for a sustained period of time at a frequent intensity, meaning they will have to work aerobically. As if they used any other system, they wouldn't be able to get the right amount of ATP and energy they need for the activity. By using the aerobic energy system, it also helps provide the working muscles with oxygen and remove lactic acid. We would be able to see if the aerobic system was the main one used if there is a decrease in the lactate levels and an increase in oxygen levels. This is because more oxygen would be consumed and help get rid of the lactic acid, which prevent a build-up of lactic acid. The aerobic energy system would be used as it is able to be used for a continuous amount of time, which will happen in steady state exercise. It can work for a long period of time at a fairly low intensity, such as steady state. It would produce 38 moles of phosphate, and this would be enough energy to be used for up to an hour. As a result of this, the aerobic energy system would be the main energy system used during steady state exercise. The reference for this was also Pearson Schools and FE colleges. Aerobic energy system. There are three stages to aerobic energy system. These are aerobic glycolysis, Krebs cycle, and the electron transport chain. Stage 1. Aerobic glycolysis. If there is no